Usually when we talk about a medical diagnosis,
Yeah.
there's this expectation of, well, absolute precision.
Oh, sure. Yeah.
Like it feels like engineering almost.
Yeah.
You break your arm, the x-ray shows that jagged white line, and the doctor just points at it and says, there it is.
Right. It's binary. It's clean. The evidence is just right in front of you.
Exactly.
Yeah.
And it's incredibly comforting. I mean, we like things to be visible, to be neatly categorized.
Definitely.
But then you step into the world of how human knowledge actually works.
Yeah.
Like how we connect facts,
Mhm.
historical events, cultural trends, or, I don't know, even just who starred in what movie. And suddenly that clean x-ray machine is completely broken.
Oh, completely shattered.
Right.
Yeah.
We're looking at a landscape that is just incredibly murky and chaotic. And that is exactly what we are decoding today in this deep dive.
Yeah, it's a fascinating one today.
It really is. We're looking at a breakthrough 2026 paper from ACM Multimedia that basically finally teaches artificial intelligence how to read those messy real-world x-rays of human knowledge.
Right.
We are diving into an architecture called M2GDT and how it is fundamentally changing the way AI systems manage, predict, and reason over just massive amounts of contradictory information.
Yeah.
And doing it without hallucinating.
And that acronym, M2GDT, it stands for MLLM-Guided Diffusion Transformer with Relation Adaptive Mixture of Experts.
Oh, well.
Yeah, it is definitely a mouthful.
Oh, yeah.
But we are going to break down why the mechanics behind it are so elegant. Because this paper is tackling what is arguably the single most critical bottleneck in AI right now.
Right, because we all know AI can, write a convincing poem or generate a pretty picture.
Exactly. But getting it to actually reason across different types of messy data to find a factual truth, that is notoriously difficult.
Yeah.
So to understand why this model is such a massive leap forward, we first have to ground ourselves in something called a multimodal knowledge graph.
Okay, let's unpack this.
Yeah.
Because I feel like when most people hear the term knowledge graph, they probably just picture a giant text database.
True. Yeah, like Wikipedia or something.
Yeah, exactly. Something like Wikipedia, but maybe formatted as a giant spreadsheet so a machine can read it.
Yeah.
Just endless rows of text pointing to other text.
Right, and that is a traditional way of doing things, yes. But a multimodal knowledge graph is a completely different beast, and it mimics human cognition much more closely.
Okay.
It doesn't just link text to text. It links underlying structural relations, textual descriptions, and rich visual cues all together in this massive interconnected web.
So if we imagine a single point of data, right, like a node for the actress Reese Witherspoon,
Okay, good example.
in a standard old-school graph, it might just have a text link pointing to another text node that says she acted in the movie Water for Elephants.
Precisely, just text to text.
Right.
But in a multimodal graph, that acted in relation is structurally linked to a high-resolution photograph of her.
Oh, I see.
It's linked to a dense textual plot summary of the film. It might be linked to the visual movie poster or even an audio snippet. So the graph isn't just a list of facts. It is a multidimensional representation of knowledge.
Which sets up the exact problem these researchers are trying to solve.
Yeah.
The task is called multimodal knowledge graph completion.
Yes, MKGC.
Basically inferring the missing pieces of the web. You give the AI a head entity, a specific relation, and you ask it to fill in the blank.
Right.
You say Reese Witherspoon acted in, and then just a giant question mark.
Yeah.
And the AI has to sift through this massive web of text, images, and structural math to find the answer.
And it has to use all of those available data types simultaneously to figure out that question mark. It can't just rely on the text.
Okay, it makes me think of trying to solve a really complex murder mystery, but your clues are in 3 completely different formats.
Oh, I like that.
Yeah, so you have a blurry photograph from a security camera, you have a handwritten transcript from an unreliable witness, and you have this abstract mathematical family tree showing how everyone in the town is related.
Right, right.
If you want to find the missing piece, the identity of the suspect, you have to use all 3. You can't just look at the photo, or you'll miss the motive that's hiding in the family tree.
The murder mystery is a great way to look at it, actually. And it highlights why you, as someone navigating an increasingly AI-driven world, should care about this specific puzzle.
Yeah.
Because the future of AI isn't just about generating text that sounds confident and plausible.
The hallucination problem.
Exactly. It's about building systems that can actually fact-check themselves. Systems that can look at messy, contradictory, multimodal evidence and arrive at a factual truth rather than just guessing.
But that raises a massive question for me. If we have all these amazing clues for the AI, the high-res photo, the text transcript, the structural family tree, Why is it so hard for the AI to just fill in the blank? I
Well,
mean, if the data is there, shouldn't the machine just see the answer? It feels like there must be a massive language barrier happening under the hood.
there is. And the researchers identified two deeply coupled difficulties that have plagued every model before this one.
Okay.
The first is exactly what you just inferred. They call it cross-modal semantic heterogeneity.
Oh, boy.
Yeah, big words. But think about the clues in your murder mystery. The visual data in an AI is typically encoded by a vision model, something like ResNet 50.
Okay.
The text is processed by a language model like BERT, and the structural graph data is encoded by topological models like Tucker.
And because they are different models, they don't process the world the same way at all.
Not at all.
The vision model is basically looking at edges, pixels, and color gradients.
Right.
The text model is looking at the proximity of words in a sentence.
Mm-hmm.
And the structural model is just doing pure relational math.
Exactly.
They might as well be speaking different languages.
Yeah.
The vision model is speaking French, the text model is speaking Japanese, and the structural model is speaking algebra.
Yes, and the mathematical incompatibility is severe. Even when the vision model and the text model are describing the exact same entity, say an apple, they occupy completely different mathematical spaces. The text model defines apple by its relation to words like fruit or orchard,
Right.
but the vision model defines apple by its round shape and red pixels.
Gotcha.
Comparing them directly is incredibly noisy. So that is challenge one.
Which leads to challenge 2, which the paper calls relation-dependent multimodal cue selection,
Yes.
meaning you can't just weigh all the clues equally every single time. The importance of the clue depends entirely on the relation you are looking for.
Exactly. If the relation you are trying to solve is who is married to who, that abstract family tree structure might be the only clue you actually need.
Oh, right. The visual photograph is probably irrelevant there.
Right. But if the relation has the same architectural style as, well, the family tree is useless.
Yeah, you desperately need the visual context of the buildings to make that connection.
Exactly. So the AI has to dynamically figure out which clue matters most while the clues are all speaking different languages.
Wow. Okay, so how did the older previous generation systems handle this? Because I know people have been using diffusion models, the same underlying tech that powers AI image generation, to try and solve these graphs for a while now.
The old way was incredibly blunt. Prior diffusion models essentially took all the raw, heterogeneous features.
The French, the Japanese, the algebra.
Yes, mashed them together into one giant vector and shoved them directly into a diffusion denoiser.
Wait, really?
Yeah, they implicitly assumed that the AI's neural network was powerful enough to just sort out the translation and the cue selection on the fly, while it was simultaneously trying to generate the final answer?
Wait, so previous models essentially threw the photograph, the transcript, and the family tree into a blender, hit puree, and just hoped the AI could somehow unmix the smoothie while simultaneously solving the murder mystery.
The math actually reflects your blender idea perfectly.
Oh.
What's fascinating here is that by forcing a single denoising process to do everything at once, selecting the right clues, translating the semantic languages, and generating the structural entity, it created massive entanglement.
I bet.
The AI is essentially trying to paint a masterpiece while simultaneously trying to manufacture the paint, invent the concept of color, and build the canvas at the exact same time.
That sounds impossible.
It introduces incredibly noisy, semantically inconsistent conditions for the model, which just leads to terrible performance when inferring complex facts.
Which brings us to the core breakthrough of this 2026 framework. The M2GDT model realizes the blender approach is fundamentally broken, so it introduces a completely decoupled paradigm.
Right.
They call it align then diffuse. It's about separating the workflow. You don't blend everything.
Yeah.
First, you sort the clues. Second, you translate them. And only then do you try to solve the mystery.
Exactly. And that first step, sorting the clues, is handled by an architecture called the Relation Adaptive Semantic Routing Mixture of Experts,
Right.
or RSRMO for short.
Okay, RASRMO is a heavy piece of jargon.
Yeah.
But if we break it down functionally, it's basically a dynamic switchboard, right?
That's a great way to visualize it. Instead of a uniform brute force fusion of all the data, this system uses a router.
Okay.
When a query comes in, the router looks at the specific relation being asked about, say, architectural style, and it dynamically routes the data to the best modality-specific expert networks.
I see.
It mathematically suppresses the irrelevant noise, like the text or the structural math, and heavily highlights the visual semantic paths that actually matter for that specific query.
Okay, but I have to push back on this a little bit, because anytime we talk about a mixture of experts in AI, there is a known trap.
Yep, you're thinking of mode collapse.
Exactly. If you have a bunch of subnetworks, these experts dedicated to analyzing the visual clues, neural networks have a notorious habit of getting lazy.
They do.
Wouldn't all these visual experts eventually just learn to do the exact same basic analysis to minimize their computational effort? I mean, making the whole mixture part completely pointless.
It goes even deeper than that. They won't just get lazy, they will actively mimic each other because it's the path of least resistance during training.
Right.
But the researchers anticipated this exact mode collapse. They realized you have to force the experts to stay diverse. So they introduced a very clever mathematical penalty system based on something called a CLUB-style regularizer.
Okay, so without getting bogged down in the raw calculus, how does that penalty system actually force them to do different jobs?
Think of it as a workplace mandate.
Okay.
The system actively penalizes the overall model if the experts within the same modality start producing the same mathematical representations.
Oh, I see.
It explicitly forces them to capture complementary information. So within the visual modality, one expert is mathematically forced to specialize in identifying colors, while another is pushed to exclusively analyze geometric shapes.
Wow, they are banned from redundancy.
Exactly.
And at the same time, the paper mentions they use a specific reward system, a binary cross-entropy loss, to ensure that even while they are hyper-specializing in colors or shapes, they don't lose sight of the actual murder mystery.
Right, they have to stay focused on finding the right missing entity.
Gotcha. So the router sorts the clues, and the experts refine them perfectly without overlapping.
Correct.
Okay, so the router has done its job. We have avoided the blender. We've perfectly refined clues based on the specific relation. But we still have that massive first problem.
The language barrier.
Exactly. The clues are still in different languages. We have highly refined French, perfectly articulated Japanese, and exquisite algebra. But they still can't talk to each other.
Right.
How does the model actually translate them into a unified understanding without losing the original meaning?
Well, this is where we move to the alignment phase, which is arguably the most elegant technical achievement in the paper. To get all these modalities to speak the same language, you need a universal translator. And for that semantic anchor, they used a massive multimodal large language model, specifically Qwen3VL.
They use a massive LLM. But as I was reading the paper, a huge detail stood out to me. They use a frozen anchor.
Yes, they do.
Meaning all the massive parameters and weights of that Qwen backbone are completely locked throughout the entire training process of the new model.
That's right.
Why use a frozen anchor? I mean, my intuition says you'd want the MLLM to learn and adapt alongside the rest of the model so they can grow together. Wouldn't a flexible translator be better?
It's a very common assumption to want everything to learn simultaneously, but think about what an anchor actually does in the physical world.
Okay.
If you tie your boat to an anchor and that anchor is drifting with the tide, your boat is still lost at sea.
Oh, that makes sense.
If the massive MLLM is constantly updating its weights and shifting its internal representations during training, the unified semantic space it's trying to create for the other clues is constantly moving.
Ah, so it's a moving target. The vision and structure models would be trying to translate their data into a language that is changing its vocabulary every 5 seconds.
Exactly. By keeping the MLLM frozen, it provides a stable, immovable ground truth.
A fixed coordinate system.
Right, a fixed coordinate system of human knowledge that the other modalities can reliably map themselves onto.
That makes perfect sense conceptually.
Yeah.
But mechanically, how do they actually pull the other modalities toward this frozen anchor?
They use a combination of mathematical alignment techniques like cosine similarity and KL divergence.
Okay.
But conceptually, you can think of these as elastic rubber bands.
Rubber bands.
Yeah. The system calculates the mathematical distance between the sorted visual clues and the frozen language anchor.
Got it.
If the visual clues drift too far away from the profound cross-modal understanding locked inside that frozen Qwen model, the mathematical rubber band snaps them back into alignment.
Oh, wow.
It penalizes the model until the French and Japanese are properly translated into the anchor's universal space.
But you have to be careful with rubber bands. Right. Because there is a massive warning in the paper about this specific step. They explicitly warn against overalignment.
They do, and they proved it quantitatively by tracking that cosine similarity during training. It's a fascinating balance.
Yeah.
If the alignment is too loose, say the mathematical similarity is below 0.50, the modalities remain fragmented. The rubber band is too slack, the translation fails, and the clues still can't talk to each other.
But if you tighten the rubber band too much,
If the alignment gets too high, pushing above 0.60, the model actually begins to suffer from semantic collapse.
meaning,
It loses its structural specificity.
oh, because it becomes completely homogenized.
Exactly.
It's like translating a very precise algebraic equation into a beautiful, flowing poem. You might capture the vibe of the math, but you lose the precise, rigid graph relations that you actually need to solve the problem. The math gets washed out by the broad language semantics.
That is spot on. The researchers found that the optimal convergence, the absolute sweet spot, is a similarity score strictly between 0.52 and 0.58.
It's the Goldilocks zone of artificial reasoning.
Yes.
Just aligned enough to understand each other perfectly,
Yeah.
but not so aligned that they lose their unique modality-specific identities. I love that.
It's really clever.
Okay, so now we have our clues completely sorted by the router, and they have been translated into a unified semantic space without losing their edge.
Yeah.
Now, and only now, do we bring in the diffusion model to actually generate the answer.
Right. The Knowledge Graph Diffusion Transformer, or KGDT.
Okay.
Now that the data is aligned and clean, the diffusion denoiser doesn't have to worry about cue selection. It doesn't have to worry about translation.
It's free.
It is completely unburdened. It can focus 100% of its computational power on graph condition generation.
And when we say generation here, we aren't talking about generating a picture of a cat. We are talking about sculpting a mathematical entity out of pure noise.
Yes. Starting from pure random Gaussian noise, the transformer takes 100 iterative steps.
Wow.
At each step, guided by those perfectly sorted and aligned clues, it shaves away the mathematical static, slowly resolving the noise into the exact multidimensional representation of the missing entity in the knowledge graph.
It scarps the truth out of the static.
Yeah.
That is incredible.
Yeah.
With an architecture this decoupled and purposeful, I have to imagine it absolutely crushed the older Blender models on the academic benchmarks.
It did.
But usually when you add complex things like dynamic routers and frozen anchors, a model can become incredibly brittle in real-world testing. Did the complexity actually pay off in the data?
The results are actually staggering for a benchmark at this level of maturity. They tested M2GDT on 3 of the major highly competitive datasets,
Okay.
MKGW, MKGY, and DB15K. It beat 19 different baseline models.
19.
Yeah. To put this in perspective, let's look at the MKGW dataset. The previous state-of-the-art model was called MCKGC, and it had a mean reciprocal rank, or MRR, of 36.88. This new model bumped that up to 37.77.
Almost a full point increase. Now, if you aren't living in the academic machine learning trenches, a 0.89 increase might sound like a rounding error.
Sure.
But when you are already in the high 30s on these complex reasoning tasks, a full point jump is monumental. Teams will spend millions of dollars in compute just to fight tooth and nail for 0.1%.
Oh, absolutely. And it isn't just the overall rank. It also completely dominated the top-tier precision metrics, like hits at 1.
Okay, what does that mean practically?
This is crucial for real-world application. It means that when the model is absolutely confident about its #1 guess, its accuracy is drastically higher than prior models.
Oh, wow.
It is getting the exact missing entity right on the very first try, rather than just burying the correct answer somewhere in its top 10 guesses.
But whenever I see a system this beautifully complex, I immediately want to start pulling out the Jenga blocks. Yeah, I want to know which part of the machine is actually doing the heavy lifting. Do they do an ablation study where they intentionally turn off parts of the architecture to see what makes it break?
They did a very thorough ablation study, and the results definitively prove their hypothesis.
What did they find?
Well, for instance, if you remove the structural branch, if you take away the mathematical family tree from your murder mystery analogy, performance degrades significantly.
Make sense?
The MRR drops from that high of 37.77 down to 35.12.
Which proves you can't solve a relational mystery without the relational map, no matter how good your photos or text transcripts are.
Exactly. But the most severe collapse happened when they targeted the router.
Oh.
When they removed the RESRMO system, forcing the model to go back to the old way of just uniformly blending all the clues, regardless of the relation.
The blender.
Yes, back to the blender. The MRR absolutely plummets to 30.88.
Wow. It completely falls off a cliff.
Yeah.
Dropping all the way to 30.88 essentially turns it into a Legacy model.
It does.
That proves that throwing things in the blender really is the worst way to process multimodal data. If you don't carefully sort and route the clues based on the specific relation first, the entire reasoning system just falls apart.
It completely validates the core premise of the paper. You simply cannot entangle clue selection, semantic alignment, and entity generation.
There was one final generalization test they ran, though, that I found truly mind-blowing.
Oh, really?
Because it challenges how we think about the role of large language models. They wanted to prove that the genius of this system was the align then diffuse pipeline itself, and not just the fact that they were using a massive cutting-edge language model like Qwen3VL as the anchor.
Right.
So they intentionally handicapped the system.
They did. They completely removed the massive Qwen3VL model and replaced it with CLI-VIT-L14.
Right.
Now, CLIP is an older, fundamentally different, and arguably much less capable model when it comes to deep, nuanced language understanding.
So they swapped out the state-of-the-art engine for an older, smaller one. And what happened to the reasoning performance when they downgraded the semantic anchor?
It barely moved.
Really?
Even with the older CLIP anchor, the performance only dropped to 36.85 MRR.
36.85, which means even with a downgraded engine, it is basically still tied with the absolute best previous state-of-the-art models that were trying their hardest with massive compute.
Exactly. It proves that the architectural paradigm, the act of decoupling the process into routing, aligning, and then diffusing, is a robust, highly transferable foundation.
Wow.
The heavy lifting is being done by the elegant structure of the pipeline, not just brute force by the sheer size of the language model. And that means this framework can easily be adapted to whatever the next generation of multimodal backbones happens to be next year.
So to summarize this incredible journey we've just been on, for years, AI developers have been trying to solve these complex webs of human knowledge by throwing raw text, images, and structural math into a blender, crossing their fingers and hoping a diffusion model could somehow sort it out.
Right.
And this 2026 paper definitively proves that we have to stop the blender.
Put the blender away.
Yes. By dynamically routing the clues based on this specific relation, mathematically aligning them to a stable, frozen anchor, just enough so they understand each other without losing their identity, and then unleashing the diffusion model to generate the answer, AI can infer missing facts with unprecedented accuracy.
And if you're wondering why you should care about this in your daily life, it goes far beyond scoring higher on an academic benchmark.
Yeah, why does this matter to the average person?
This architecture brings us remarkably closer to AI systems that can actually fact-check themselves in real time.
No more hallucinations.
Exactly. Imagine an AI assistant that doesn't just read your text prompt and confidently guess an answer based on statistical likelihood. Instead, it actively cross-references a structural database, analyzes supporting visual evidence, aligns the semantic meaning of all those different data types, and provides an answer that is fundamentally grounded in real-world multimodal evidence.
That kind of verifiable accuracy is the holy grail of reasoning AI.
It really is.
It totally changes the game from generating plausible fiction to deducing actual reality. And it leaves me with this final provocative thought.
Okay.
We have been talking about this entire process like a murder mystery, right? Filling in a blank that we already know exists, missing facts in a graph we've already built.
Right.
But if a model like M2GDT can now accurately predict and generate missing nodes across a multimodal web of human knowledge, what happens when these systems become powerful enough to generate entirely new, undiscovered structural connections? Right. Could a reasoning system this precise eventually act as an automated scientific researcher? If you pointed at the messy, multimodal clues of quantum physics, evolutionary biology, or ancient history, could it discover new relationships, new physical laws, or historical realities that human beings haven't even thought to look for yet?
That is a wild thought.
The blender is broken, the clues are perfectly aligned, and the AI is finally ready to solve mysteries we haven't even written yet.